There's a widely found mineral that creates a cooling effect when heat is applied to it. It sounds impossible at first. Heat is added, yet the result is cold. Cold enough to freeze water into ice using nothing more than sunlight or waste heat that would normally be discarded. No compressor is involved. No freon is used. No electrical power drives the cooling process at all. The material is called zeolite, and it is not just a theory confined to laboratories. It already appears in practical devices today. Entire structures have been cooled using it. There were even refrigeration systems capable of producing ice in desert sunlight using only this mineral. Over time, however, this straightforward method was largely set aside. The question then becomes how a rock can transform heat into cold, and why it faded from common use in home cooling systems. The concept of producing cold without mechanical compression predates modern refrigeration technology. Understanding it begins with a behavior that seems almost unreal. Certain materials generate heat when they absorb water vapor, then become cold when they release it. Many people never consider this, yet some everyday appliances already rely on this principle. Certain modern dishwashers include a small section filled with a mineral that absorbs moisture from air during the wash cycle, warming in the process, then later releases that stored energy to dry dishes without a traditional heating element. This mineral functions by continuously exchanging water vapor with the surrounding air. It belongs to a group of materials that engineers have studied for more than 100 years because of what this behavior enables. If a substance can absorb water vapor while releasing heat, then reversing the process allows it to produce cold. This is the foundation of absorption refrigeration. It is not a new idea. Its development traces back to the earliest stages of refrigeration technology, alongside early ammonia-based cooling systems. The difference is that instead of a moving liquid inside a compressor system, the process takes place within a solid material. This solid material enables something unusual. It can generate cooling directly from heat alone. No motor is required. No compressor is needed. Only the material, water, and a heat source are involved. Engineers have built solar-powered refrigerators based on this principle, capable of producing ice under intense sunlight. Other systems have used it to cool buildings using waste heat that would otherwise be lost. The technology is functional and proven. At the center of it is a mineral with exceptional properties for this process, zeolite. To understand its behavior, it helps to recognize that much of its structure is empty space. Zeolite is an aluminosilicate composed mainly of aluminum, silicon, and oxygen. It occurs naturally in regions where volcanic ash interacts with water over long periods of time. It can also be synthetically produced with carefully controlled structures. Its most important feature is not its chemical composition, but its microscopic architecture. Zeolite contains a vast network of pores and channels, forming an internal structure like a dense labyrinth. Because of this structure, a single gram contains an enormous internal surface area. A small amount can hold hundreds of square meters of internal surface. A quantity small enough to fit on a fingertip can contain more internal area than a large room floor when unfolded. Each of these microscopic surfaces can capture water vapor from the air. This makes zeolite one of the strongest desiccants known in science. It behaves like a highly advanced moisture absorber, similar in principle to materials such as calcium chloride, but operating through a different mechanism. Instead of dissolving into liquid as it absorbs moisture, zeolite traps vapor within its internal structure. It holds on to water molecules with extreme strength. In some advanced systems, calcium chloride is placed inside the pores of zeolite, creating a combined material that performs even more effectively than zeolite alone. The mineral framework and the salt work together as a highly efficient moisture-absorbing system. A strong desiccant alone is not enough to create refrigeration. The cooling effect appears when the movement of water is considered. Whenever water evaporates, it removes heat from its surroundings. This is why a wet surface feels cold when air passes over it. As water turns into vapor, it carries energy away. However, normal evaporation has a limit. As air becomes saturated with moisture, it can no longer accept additional vapor. Once this saturation point is reached, evaporation slows and cooling stops. Zeolite changes this limitation. Imagine a sealed chamber containing a small amount of water on one side and zeolite on the other, with all air removed. As water begins to evaporate, the zeolite immediately captures the vapor molecules. The surrounding space never becomes saturated because the vapor is continuously absorbed. Evaporation continues without interruption. And as long as evaporation continues, cooling also continues. The water is driven into continuous evaporation at an accelerating rate. Each molecule that leaves the liquid removes heat with it, steadily lowering the temperature of what remains. The drop continues until the water approaches freezing and can go beyond it, becoming cold enough to form ice. The zeolite, through its extreme moisture attraction, forces the water into a rapid cooling process. This is the stage where cooling is actively produced. This is the phase that generates cold. However, the zeolite does not remain active indefinitely. Eventually, it becomes saturated with water. When this happens, its absorption capacity weakens, and its ability to draw in moisture declines. At that point, the cycle must be reset. The reset process requires heat. The saturated zeolite is exposed to thermal energy coming from sunlight, a flame or industrial waste heat. This applied heat drives the stored water out of the material, releasing it as vapor. That vapor is then removed through condensation. Once the material has been dried again, its absorption capability returns. It becomes ready once more to generate cooling. This completes the full cycle. Cold is produced when water evaporates into the moisture-hungry mineral, and the system is reset when heat removes that stored water. The concept is simple in structure. The question is whether such a material can truly cool large buildings. In practice, it already does. Commercial systems exist today that use zeolite-based water absorption chillers. Their cooling capacity ranges from around 100 cows up to several hundred cows, enough to air-condition large commercial facilities. These are not experimental prototypes. They are operational machines in real-world use, providing cooling to active spaces. The key detail is the type of heat these systems require. They operate using hot water at temperatures as low as 50 to 90 degrees. This is low-grade thermal energy. It is the kind of heat produced as waste from factories, engines, and power plants, which is typically released unused into the environment. Zeolite cooling systems take this discarded heat and convert it directly into air conditioning output. The same principle can be powered by waste heat from engine exhaust, power plant emissions, or direct solar input. The implication is straightforward. Energy normally treated as waste can be redirected into cooling systems for buildings. The same principle also scales downward. Researchers have developed solar-powered zeolite refrigeration units capable of producing ice using only solar heat. These systems have been tested in extreme environments, including regions of the sub-Saharan desert. A refrigerator operating in desert conditions can generate ice using the heat of sunlight in one of the hottest environments on Earth. Performance continues to improve over time. When calcium chloride is infused into zeolite, forming a composite material, the efficiency increases significantly. This combination reaches a coefficient of performance of up to 0.78 compared to plain zeolite systems. Newer zeolite-based materials have pushed this value closer to 0.85. A critical advantage of these systems is their lack of moving mechanical parts. With minimal mechanical wear, maintenance requirements are greatly reduced, allowing long operational lifespans. Despite this, the system must be understood clearly. It is not a perpetual cooling device. It is a heat-driven cycle. It produces cold only when absorbing water, and it must be recharged with heat before it can operate again. Heat sources may include sunlight, flames, or waste heat streams. The principle is efficient because it can use energy that would otherwise be discarded. However, a thermal input is still required. Another constraint is structural. The system requires a sealed vacuum environment. High vacuum integrity is essential for proper function. The process depends on a near-empty chamber where vapor transfer between water and zeolite can occur without interference. Even small leaks can disrupt the system entirely. Efficiency is another factor. When measured strictly by energy input, zeolite cooling systems typically show a lower coefficient of performance compared to modern electric compressor-based systems. However, this comparison changes when considering energy source. Zeolite systems operate on free or waste heat rather than purchased electricity. In that context, lower efficiency relative to electrical systems does not prevent practical usefulness. A further limitation is market structure. There are few manufacturers producing these systems, and available units are expensive. This creates a cycle of low production and low demand, reinforcing high costs and limited adoption. None of these limitations mean the technology fails. The systems operate continuously in real-world conditions. The constraints define its role rather than its feasibility. Still, these trade-offs are not the primary reason zeolite cooling is uncommon in residential use. The deeper reason lies in economic structure. The systems did not fail because they are ineffective. They were outcompeted by technologies that could be packaged, controlled, and sold repeatedly as commercial products. Zeolite cooling depends on freely available inputs such as sunlight, industrial waste heat, and residual thermal energy from engines and factories. These are energy sources that are often discarded rather than monetized. Its entire breakthrough lies in converting freely available or wasted energy into cooling power. But viewed through the perspective of an industry built on selling cooling as a continuous service, that becomes a problem. Free sunlight is not a revenue stream. Wasted heat cannot be billed. There is no way to attach a meter to the sun. In contrast, the electric compressor became the ideal commercial product. It is compact, sealed, and capable of being patented. Most importantly, it operates on electricity, a metered resource that generates continuous income every hour it is used. Every home running a compressor becomes a long-term paying customer. Every home that could instead rely on free waste heat represents a lost opportunity for recurring revenue. For that reason, the decision between technologies was never only about performance. It was about what could be sold consistently. As a result, compressor-based systems became the standard in residential cooling. Meanwhile, zeolite-based cooling, which operates using discarded energy, was pushed into limited industrial applications and largely removed from mainstream use. Its most important advantage, the ability to use wasted heat, was treated as a minor curiosity rather than a major breakthrough. However, in regions where electricity is limited or where waste heat is abundant, the technology has continued to demonstrate its effectiveness. With rising energy costs and increasing attention on heat recovery, interest in the system is returning. The material is being re-examined. It is not disappearing. It is being rediscovered. The systems were never truly abandoned. They simply shifted into environments where free heat is valuable and accessible. Now they are positioned to re-enter broader use. One example already exists in everyday appliances. Certain modern dishwashers use zeolite compartments to dry dishes at the end of a cycle. No external heating element is required. The material releases heat it previously stored, completing its cycle within the appliance itself. Anyone using such a device already has a small working example of the technology in their home. At a larger scale, commercial zeolite-based water absorption chillers are already in operation. These systems cool entire buildings using hot water generated from solar collectors or industrial waste heat. Their cooling capacity can reach hundreds of kilowatts, enough for full commercial air conditioning systems. They operate using energy that would otherwise be discarded. Beyond that, experimental and field-tested solar-powered zeolite refrigerators have been developed. These units can produce ice using only solar heat. They have been tested in extreme environments, including the sub-Saharan region. In these conditions, refrigeration is achieved using only the heat of the sun. Development continues. The integration of calcium chloride into zeolite structures has become a key advancement. This composite approach increases efficiency and pushes performance higher, moving the technology closer to wider practical deployment. However, this is not a simple do-it-yourself system. It depends on sealed vacuum chambers and precise engineering. For most people, building such a system at home is not currently realistic. The practical approach is to recognize where the technology already exists, to observe how absorption chillers and solar thermal systems are being deployed, and to follow its continued development. As global energy costs rise, systems that utilize wasted heat are becoming more relevant. The material is gradually moving back toward broader application. What exists today is already significant. A proven cooling method operates without moving mechanical parts, using solar energy and waste heat that would otherwise be lost. It cools buildings in real time. It produces ice in off-grid desert environments. It requires no refrigerant, no compressor, and no direct electrical input for the cooling process itself. This alone represents a major technological shift in cooling systems. What lies ahead is even broader, as energy becomes more expensive and wasted heat is increasingly recognized as a usable resource. Research and industry are returning to zeolite in its advanced composite forms. It is no longer a forgotten concept. It is re-emerging with improved materials and renewed relevance. The principle remains unchanged. Cooling has always been present inside common minerals, accessible through waste heat or sunlight. The ability to transform discarded heat into usable cold has existed throughout. The only limiting factor was economic structure. Energy that cannot be measured or billed does not easily fit into traditional commercial models. Sunlight cannot be metered, and waste heat has no billing system attached to it. Yet the potential has always been there. The sun provides continuous free energy. Waste heat is abundant. The cooling capability has existed within reach the entire time. The determining factor has always been who benefits from the system being sold and measured versus those that rely on free energy sources. The direction moving forward is clear. Technologies that use wasted energy are returning as energy demand increases. This is part of a larger shift toward rediscovered methods becoming relevant again, strengthened by new materials and modern engineering. The cycle is closing back on itself. What was once pushed aside is returning. The future of cooling is not only about new inventions, but also about re-examining what was already possible. Stay aware of where this technology is heading and follow the developments as they continue to evolve. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.